Hi guys, this is Miss V and I'm back with our lecture on rate of reactions. So as you remember on the last lecture we did energy of reactions. Well, now we're going to go into how we can change the rate of reactions. So let's look back and we'll do a little review before we get started. So remember, I always have told you guys, you cannot forget what happened in the first semester. So in that first semester, we talked about our gas laws, and we talked about the relationship between pressure and temperature, pressure and volume. If you remember our three gas laws that we used Boyle's, we used Gay-Lussac's, and then I'm going to probably forget that third one. But if we remember, we had one that was pressure and temperature, and that was a direct relationship. That means as pressure goes up, temperature goes up. And then we had another one, pressure and volume, where when pressure goes up, volume goes down, okay, or the vice versa. Well, now we're going to add in something else, and we're going to talk about pressure and number of collisions. And we talked a little bit about it back in the gas laws, but pressure and number of collisions will also have a direct. As we increase the pressure, the number of collisions will increase. And as we decrease the pressure, the number of collisions will also decrease, okay? And we'll look at a picture in a minute, but just remember that most of the time when we're talking about these reactions, we're talking about pressure and number of collisions, and we're really talking about how we change those number of collisions, and we'll talk about each way that we can as we go forward. All right, a couple definitions before we get started. Number one, like from our last lecture, we talked about the activated complex. So that is the actual top of our graph. And so that's where we have our activation energy, which brings us up to the top of our graph. And at that activated complex we talked about, that is the point where that first chemical reaction begins. If you remember when I did the demo, when we made the water in the balloon in class, that flame gave us that activation energy, which brought us right to that activation complex, and then it took off from there, and that's where we saw the big boom and kind of the fireball when it went off when the water was made. Okay, the other thing we'll talk about, you may have noticed in the lab, was surface area. So the surface area, if you watched the rate of reactions lab that was here, it used chalk. And so surface area is just the amount of area that is exposed of the reactant. So how much exposure does the reactants have? And we'll look at a couple pictures and graphs of that as well. The next one we're going to start talking about is mixing. And mixing really means stirring or shaking of the reactants. You may have seen me do that when we made the hydrogen peroxide, kind of swirled it a little bit when we're making the water. Next one, I'm going to remind you one more time, is temperature. Remember, temperature kind of measures the average kinetic energy of the reactants. Remember, energy or heat and temperature are two different things. They're separate. Temperature really just tells us how fast are those reactants moving. And that's how we kind of gauge it, by taking the temperature. Remember, kelvins, if they're not moving, it's measured in kelvins. If they're not moving, we're at 0 degrees Kelvin. And that is just a theoretical one. Remember when we talked about that last semester, that we never have seen anything stop moving completely, but we kind of say there is a theory of a 0 Kelvin. Okay, concentration is our last one, and is the amount of reactants or atoms in a mixture. And we'll see how concentration kind of makes a difference. All right, what are we talking about? We're really talking more about how can we affect collision theory, or what is collision theory. Okay, it is to have a reaction occur, atoms must collide with each other. So you can't have a reaction unless the atoms actually collide with each other to make it work. Remember, I told you guys, in those bonds is a bunch of energy stored no matter what. And so you must have some kind of energy to make them split apart, okay? And then make new molecules. So we have to have some kind of collision in the reaction. So here, right here, you see a nice combustion reaction here. You are seeing right here that all the reactants are now colliding, and so it causes these products to be made, such as the fire and CO2, and probably some water too, as we know that's what comes out of a combustion reaction. Okay, so when those reactants collide, they must have enough energy to get to that activation complex to cause the reaction to occur. So as they're just sitting here, la 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 la, they're not really colliding very much. But once we start adding energy, this is when they start colliding. Go, 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 bam. Now we've hit that top of that energy, and now they're colliding so much, now we're having the reaction happen. And that's where we go down, and we're releasing that energy in that exothermic reaction, okay? So, again, I'm going to use the example of making the water demo I did in class, okay? Those atoms were very, very happy inside their balloon until I added a little bit of energy, started moving them a lot faster, and then those first ones collided and caused that exothermic reaction to create, and we got water. All right, how to change the number of collisions? How can we increase? Because that's really our goal here, is to increase the number of collisions so we get the chemical reaction to occur. Well, the first one we'll talk about is surface area. So you can see right here, this is kind of a difference of surface area. So if we increase the surface area of the reactants, more area for those atoms to come in and collide. You notice here with a box that's really tightly bound, we can't really get to those middle ones. So you see the other reactant out here, and it can't really get to those. It can only access the ones on the outside. But if we break this apart or crush it, such as they did with the chalk, now the chalk is in smaller pieces. It's still the same molecule, but it's in smaller pieces, and now that vinegar can actually collide with the chalk molecules a whole lot easier. So if we increase the surface area, we're going to increase those collisions. We're going to make that chemical reaction happen a whole lot faster than if we just wait for this to happen, okay? The second thing is to mix them. So if we mix them, we're going to increase the collisions of reactants by stirring and making them closer to each other. So you can see here, we have one reactant up here, and we have one kind of hanging out down here, right? And one of the things you guys can really understand is something like salt water. If you just pour the salt in, sure, it'll slowly dissolve into the water, but if you stir it, then it starts making everyone kind of mix together, mingle together, and collide together, and making that dissolving or that chemical reaction of the salt kind of happen a little bit faster instead of just waiting for it just to happen. Same thing with sugar. If you put sugar into water and you just kind of let it hang out, eventually it's going to dissolve. But if you stir it, it happens a whole lot faster. All right, the third one we're going to talk about is temperature. So if we're increasing temperature, it increases the kinetic energy of the atoms. That means they're moving a whole lot faster. And as they move a whole lot faster, they're going to have a higher chance of actually colliding with one another. So here's our example over here. We have a fire and it's kind of starting. Well, it's kind of just hanging out. Okay, it's not really doing much, but as we started having some heat with the wood, because we really want the reaction of the combustion of the wood to happen to keep the fire going. So we started adding our heat. We made that reach the level of the activation complex. We put in that activation energy, and now look at all these molecules. They are moving all over the place. And so now we've got molecules colliding, and we're getting that combustion of our wood happen a whole lot faster than if we just sat around and just waited for it just to happen. And a lot of you probably see we add that. You can also add, and we'll talk about it in the next, a concentration. So if you blow on a fire, you're adding that oxygen as you're blowing. Yes, you're blowing out carbon dioxide, but you're also got some oxygen going in there, and you're causing that to increase the concentration of oxygen within that fire, causes that fire to burn a whole lot faster instead of just hanging out and waiting, okay? So our fourth one, which I kind of alluded to just a minute ago, is concentration. So if we increase the concentration, which is just increasing the amount of reactants in a container, it increases the collisions. The more we have, the more they're going to collide. And I always think sometimes about cars on streets, right? The more cars we have on a road at a certain amount of time, the more chance we're going to have accidents, okay? And also just like temperature, you can think of that with cars too. The faster those cars go, the more chance we're going to have collisions between cars. The same with molecules. So the faster they go, the more collisions we're going to have, The more of them we have, then we're also going to have more collisions, and we're going to get that chemical reaction to happen a whole lot faster than just sitting there and watching it. Okay, another thing we can change, we talked about, is pressure. If you remember when we played with the simulation last semester, when we kind of played with pressure and how that kind of affected things, well, if we decrease that volume, we're going to increase that pressure, and you can see they're a whole lot closer. So now our pink and green reactants here are going to collide with each other so much more often than here, because they don't have as far to go. So the more they collide, the more that reaction is going to happen, and it's just going to happen a whole lot faster. Okay, just like even if you think about cars, right? You put them in a smaller area, same amount of cars, but in a smaller amount of area, you're going to have those cars most likely hit each other more often than if they have more area. Okay, next one is energy. If we add energy, and here's another one, adding heat. Remember, heat and energy are the same thing. They are not temperature. Heat and energy are different, okay? So we're adding energy, increases the movement of the atoms, makes them go a lot faster, so then you're going to have those higher collisions. If you have those higher collisions, then you are going to have a faster chemical reaction, okay? Okay. The last kind of concept we're going to talk about today is catalysts. What the heck is a catalyst, and why would we use them? You guys actually saw me use a catalyst when we did the water demo in class. I took around and I showed most of you, hopefully you guys saw it, the decomposition of hydrogen peroxide, which is this example down here. So you saw the decomposition of hydrogen peroxide and how slow it happened just by being in the beaker. But I added what we called a catalyst. And a catalyst really is a substance that assists a reaction to occur. So that gets it to occur. That kind of is that push, okay, that causes it to start. Where the reaction is kind of like, okay, go really slow, we're good. But you add that catalyst and it's kind of like pushing them along, okay? No, you're going to do this. So it is not a reactant or a product of the reaction. It is not involved in that part at all. It may chemically change a little bit, but it's not considered a reactant or a product, okay? But what it does do is it lowers that activation energy needed. So we need to climb the hill a whole lot less. So this is a graph over here that you can see. So, and this is actually the hydrogen peroxide, okay? So if you think about it, if I would have left hydrogen peroxide on its own, eventually we would have gotten up here, true, and then we would have made our oxygen. But I may have had to sit there a very, very, very long time with the balloon, and not every class would have been able to get it. So instead what I did was I added that catalyst. That catalyst came in and it said, okay, well, we don't need as much energy to get up to this point to make this happen, because I'm just going to push this along. I'm going to help it along, and I'm going to decrease that activation energy and make us get as many products as we can faster than we can. Now, here in chemistry, I know you probably are thinking, well, how does it do that? Well, we're not going to worry about that right now. What we are going to do is we're just going to understand that it decreases the activation energy needed. Remember, some things we're going to leave for if you go into AB chemistry. This is one of them. So just know that a catalyst decreases the activation energy, okay? And I know in your questions from your reading that was on Google Classroom that you guys had to research a biological, something in your body that is a catalyst. There are tons and tons of catalysts inside your body. They're called enzymes. And basically they come in and they help make something happen that needs to happen. They push it along. So really, I just really want you guys to get that a catalyst comes in, not involved in the chemical reaction that we're looking at. So it's not a reactant or a product, but it comes in and pushes that along, and it decreases the activation energy so that we can actually make the products a whole lot faster than before, okay? Like before, if you guys have any questions, just get a hold of me and I will answer them. I hope this helped a whole lot more, and I hope you guys understand it. All right, thanks. Good night.